Hello students, welcome back to my channel. In this video, we will study about the Maxwell Boltzmann distribution law. Okay, what you are doing is we will be deriving an equation for the Maxwell Boltzmann distribution law. It can also be termed as MB statistics. MB statistic or Maxwell Boltzmann distribution law. Okay, so we will start the derivation. First, what you need to do is you need to consider a system. Okay, you need to consider a system that is composed of n distinguishable particle. Okay, here n means it is a distinguishable. Okay, distinguishable means they are all different. Okay, that means if you have two particles, that means you can distinguish between the particles. Okay, that is what I mean by the distinguishable particle. Okay, now the energy of this particular system is E. Okay, n is the distinguishable particle that is present in a system and that is having a energy E. Okay, now these distinguishable particle in a system will have certain characteristic. Okay, there are mainly four characteristics that is possessed by these n distinguishable particle. Okay, the first characteristic or property is the particles do not attract or repel each other. Okay, they do not attract or repel each other. Okay, that means they are independent of one another. That means if you consider a system, there are many particles. This particle is not under the influence of this particle. That means they are independent. They are not attracted or they are not repelled by the other particle present in a system. That is the first characteristic. Okay, they are not attracted or repelled by other particles. Next, each particles are distinguishable from other. Distinguishable particles. Okay, that is what we mentioned earlier. We are considering n particles, they are distinguishable. Okay, that is the second characteristic. Okay, third characteristic is there is no restriction. There is no restriction on assigning. There is no restriction on assigning various energy level. Okay, energy level to the particle being imposed. Okay, there is no restriction on assigning various energy level to the particle being imposed. What's the meaning? If you consider energy level, say there are many energy level. Okay, say this is E0 energy level, this is E1 energy level, this is E2, and similarly it continues. Okay, there are many energy levels, and according to this statement, in say this in this energy level there may be any number of particles. Okay, it is need not necessary that in this energy level there must be a two particle. Okay, here any number of particle can be present. Here also there can be a presence of one particle or multiple particle. Okay, there is no restriction for particle or on assigning the various energy level to the particle. Okay, any number of particle can be present in a energy level. That is the meaning. Okay, the last characteristic is these energy level, whatever we consider, no, that is all non-degenerate in nature. Okay, they are all non-degenerate. That means the energy of E0 is different from energy of E1, and similarly energy of E1 is different from energy of E2. They are non-degenerate. Degenerate means what? Same energy. But non-degenerate means the energy of the energy the energy levels are having different energies. Okay, that is what the meaning. Now these four characteristics of what? These distinguishable particle in the system having energy E. Okay, here E is the total energy. Okay, this is simply called as the Boltzmann law also. Okay, this four property or four characteristic is there, no? That is together called as Boltzmann law. Okay, so what are the four characteristics that is possessed by the particles? They do not attract or repel, and they are distinguishable from one another, and there is no restriction on assigning various energy level to the particle, and all the energy levels are having different energy, they are not same. Okay, these are the 4 characteristics. Now we will derive the Maxwell Boltzmann equation. Okay, now the derivation starts. Okay, now let us write, let n naught number of particle, n naught particle be in energy E naught. Okay, what we are assuming, in this E naught there are n naught number of particle, and similarly in the E1 level there are n1 number of particle. Similarly in the E2 there are n2 number of particle. Similarly if you consider EI, how many number of particle will be there? Ni number of particle will be there. Okay, the same thing we are writing in the statement. Okay, let n naught particle be in the energy level E naught, and n1 particle in the energy level E1. Okay, n2 particle is in the energy level E2, so on. Ni particle are in the energy level Ei. Okay, so what we are considering, in E naught there are n naught number of particle, in E1 level n1 particles are there. Similarly, if you have ith energy level, then there will be ni number of particle. Okay, and the total number of particle and the energy of the system remain constant. Okay, whatever the arrangement, but if you consider total number of particle as well as the total energy remains constant. How? Just imagine you have say 10 balls. Okay, you have 10 balls, and say you have 5 racks. Okay, these are all racks, and now I am comparing these racks to the energy level. Okay, E naught, E1, E2, etc. Okay, now let me say that there are 2 balls in the E naught rack, and here maybe 1 particle. Okay, here maybe 3 particle. Okay, now here maybe 2 particle. Here also 2 balls are there. Okay, now the distribution is different, right? In E naught the 2 number of balls are there. In E1 the single ball is there. But if you count the total number of ball, okay, that is total number of particle is 10 only, right? Irrespective of their distribution, the total number of particle as well as the total energy E, okay, E is what? Total energy, they remain constant. Okay, this thing you need to remember. Okay, the total number of particle as well as total energy of the system remain constant. Okay, even though their distribution in the different energy level is different, but total will be remains the same, right? Yes. Now let me call n is equal to, n is what? Total number of particle. Total number of particle is what? If it is if you are considering this 10 ball will be what? The number of balls in the energy level E naught plus number of balls here plus number of balls here, correct? So similarly till here you will be adding them, you will get what? The 10, that is total number. Now what we are considered in this, n naught number of particles are there, here n1, here n2 particles are there, and so on. In here it is ni number of particles. So what will be n? N will be n naught plus n1 plus n2 till ni, correct? So I can write this as summation, correct? Summation ni, where I is from 0 to I. Okay, and similarly I told the energy of the system is constant. So E is the total energy, that is given by what? E is what? E is nothing but n naught E1, E naught n1 E1 plus n2 E2 etc. ni Ei, correct? So simply this can be written as summation ni Ei, okay, where I is from 0 to I. Okay, I am calling these 2 equation as 1. Okay, I am just naming this equation as well as this equation as equation number 1. Okay, well, next the number of ways in which the number of ways in which the n particle can be put in this energy level is given by, okay, the number of ways in which n particle can be put in this energy level. In this energy level means what? E. Okay, in the energy level E is given by one formula. Let me turn the page. That is given by this particular formula. Okay, W means thermodynamic probability. Okay, W can be called as what? Thermodynamic probability. That is given by this formula. Okay, you need to remember n factorial divided by n naught factorial, n1 factorial, n2 factorial until ni factorial. Okay, this is the formula, or this is the number of ways in which you are distributing n particles in the different energy level. Okay, it is given by thermodynamic probability. Now what you do is you need to take the natural logarithm on both the side. Okay, taking ln is nothing but a natural logarithm on both the side. Okay, so it becomes ln W and ln of n factorial divided by n naught factorial, n1 factorial, n2 factorial till ni factorial. Okay, now how can you write this one? We know the property of ln, right? The ln A by B can be written as what? Ln A minus ln B. Okay, we are applying this to here. So what I get? Ln n factorial minus ln n naught factorial, n1 factorial, n2 factorial, etc., ni factorial, right? So I just applied this formula or this property to here. Okay, now once again you need to use the property of ln, that is if you have ln AB, okay, and that means if you have the product here, okay, then what you can do? Ln A plus ln B, correct? So if you have the product, okay, then ln A plus ln B. Now you are using this property here. Okay, you can see the product here, right? N naught factorial into n1 factorial into, right? So now you can split that one. Minus ln, I just open a bracket here, okay? Ln n naught factorial plus ln n1 factorial plus ln n2 factorial, etc. ln ni factorial. Okay, now I write ln n factorial minus, I can write it in the form of summation because n0, n1, n2, n3 is there now. So I can write this as ln ni. Okay, where I is from what? 0 to I. Okay, if you open this summation, you will get back this, correct? So I just represented these terms by the single terms with the summation symbol in front of it. Okay, here you have ln W. Now what you do is you will be applying the Stirling approximation. Okay, before that let me name this as 2. Okay, this is the equation number 2. Now you are using what? Stirling approximation. The Stirling approximation is used only when if you want to find the ln n factorial. Okay, if you want to find the factorial and ln of very large number, okay, where n is a very large number, okay, it is not 5 or 10, something like that. Means if you have a calculator, if you find ln 5 factorial, okay, scientific calculator, you will be able to see the answer in the scientific calculator. Okay, but if you want to find the ln 500 factorial, then you will get a syntax error in the calculator. You cannot find out the factorial and ln of very large number. Okay, so you'll get syntax error, no? So if you want to know what is the answer for this, then you will be using the Stirling approximation. Okay, so Stirling approximation means what? It is used when if you want to find the factorial or ln and factorial of very large number. Okay, So what's the formula of Stirling approximation? Ln n factorial is equal to n ln n minus n. Okay, this is the formula you need to apply here. Because why we are using Stirling approximation here? Because we consider that in the system there are n particle. So n means definitely it will be very large number, right? So that is why we will be using Stirling approximation in the MB statistics. Okay. So ln n factorial is n ln n minus n. Okay. Now what happens for the summation ln n I factorial? What will be the Stirling approximation? Summation. So here in the place of n, look here, ln n factorial, no? So here in the place of n, you have ni, correct? So wherever you have n, I write ni ln ni. Okay, summation is there because even in the left hand side you had summation. So you need to write the summation on the right hand side also. Okay, if it is not there, then what will be the answer? Ni ln ni minus ni, correct? So you are using this one. Here it is n, here it is ni. Ni ln ni minus ni. But what I am doing, since the summation was there, I will be writing summation here as well as summation here. That's it. Minus summation ni. Okay, once again I is from 0 to I. Okay, that is understood. Now I name this equation as 3 and this equation as 4. Okay, now what I do is substituting 3 and 4 in the equation number 2. Okay, what is our equation number 2? This one. Okay, in this equation we will be substituting 3 and 4. Okay, let me substitute. Ln W is equal to what? Ln n factorial, that is given by n ln n minus, okay, this minus. What we have, I just open a bracket because I don't want to get confused. Summation ni ln ni minus summation ni. Okay, now open the bracket. Ln n minus summation ni ln ni minus plus summation ni. We know that from the equation number 1, summation ni means what? It is equal to n, correct? So n ln n minus summation ni ln ni plus n. Okay, this is from what? This is from the equation number 1. Okay, just check the equation number 1. You can see that summation ni is nothing but n. Now in this you can see minus n plus n get cancelled. Left with n ln n minus summation ni ln ni. Okay, here you have ln W. Okay, W means what? Thermodynamic probability. Okay, now what you do is you will be taking or you will be differentiating this equation. Okay, differentiating above equation. Okay, this equation need to be differentiated. Okay, with respect to ni. Okay, number of particle. Okay, with respect to ni, you will be differentiating. Okay. Let me take the paper. Now let us differentiate D ln W. Here what is the differentiation of n ln n? The differentiation of n ln n is 0. Why? Because n means what? N is nothing but a total number of particles. The total number of particles we already considered that it is a constant, right? So whenever you have a constant and differentiation of that constant will be 0. Okay, the differentiation of constant is always equal to 0. Okay, then let us differentiate this. This is not 0. Okay, ni means number of particle in the ith level, right? So that is not 0. Let us differentiate this. How to differentiate this thing? So we have the general formula or a general differentiation. Suppose if you have the differentiation of x ln x. Okay, in general. Okay, if you have x ln x, that means here also you have x, here also you have the same function, right? Okay, now then what you will be doing is you will be taking this as a first function, this is as a second function. Okay, and you will be using the UV rule. Okay, UV rule for the differentiation or differentiation by parts, right? So if you use the UV rule, how it will be? You will be writing the first function as such, and you will be differentiating the second function. What's the differentiation of ln x? It is 1 by x into dx. Okay, what is 1 by x into dx? It is a differentiation of ln x. Plus, we will be writing second function ln x and differentiating first term, that is dx. Okay, so this is the differentiation of this x ln x. Okay, what you will be doing? You are writing the first function as such and differentiating the second function, plus keeping the second function as such and differentiating the first term. Okay, that is what we call UV rule or differentiation by parts. Okay, now we will be using the same thing here. Okay, why? Because you can see ni, here also ni, and you can use the UV rule. This is first function, this is second function. Okay, in the place of x, here you have ni. Okay, that is the difference. So in here, wherever you see x, no, okay, wherever you see x, no, just put ni, that's it. Okay, let me open the bracket. Ni, differentiation of ln ni is 1 by ni into dni. Okay, here it is dx, no, here now dni, plus ln x, here it become what? Ln ni into dni. Okay, so wherever you see x, substitute dni, that's it. Okay, now let me open the bracket, become what? Minus summation, ni get cancelled, you left with the dni. Okay, and minus plus minus summation ln ni dni. Okay, here you have d ln w. Now what I do is I just multiply by minus 1. Okay, multiply by minus 1 you can do minus d ln w is equal to summation dni plus summation summation ln ni dni. Now you need to write for most probable distribution d ln w is 0. Okay, for most probable distribution, d ln w becomes 0. Therefore, above equation become what? Summation dni plus summation ln ni dni is equal to 0. Okay, now note here this is also equal to 0. Okay, the summation dni. Okay, why? Because dni means what? D means what? Differentiation, correct? So ni means what? Ni can be written like this also, right? n0 plus n1 plus n2, right? So ni means number of particle. So differentiation of that particle is 0. Why? Because the particle is a constant. Number of particle we considered it to be a constant, hence dni become a 0. Okay, so we are left with summation ln ni dni is equal to 0. Okay, now I just name this equation as fifth equation. Okay, maybe it is fifth equation. Yes, it is fifth equation. Now we already considered that the total number of the particle as well as the total energy is a constant, right? So from the equation 1, I am writing this from equation number 1. Okay, so what we had n is equal to summation ni and E is equal to summation ni ei, right? This is from the equation number 1. Now since both are the number of particle and energy is a constant, if you take the differentiation, become what? It becomes a 0, correct? dn is equal to 0. Okay. Similarly, the differentiation of E is also 0. That is summation ni dni is equal to 0. Okay. So they are equal to 0. Here also you can write summation dni. Okay, I didn't write earlier. So dn or summation dni is equal to 0. Here d means what? Differentiation is equal to summation ni dei. Sorry, dei is equal to here it is ei. Okay, here it is ei. Here it is d. Let me write again. De is equal to summation ei dni is equal to 0. Okay, let me call this as equation number 6, this as equation number 7. Okay. Okay, now what you will be doing is you will be multiplying alpha and beta to the equation number 6 and 7 respectively. Okay, multiply alpha to this, beta to this respectively, and then you need to add them to the equation number 5. Okay, what you will be doing, you will be multiplying alpha to this, beta to this, and then you will be adding these to the equation number 5. Okay, so let me do it. Alpha summation dni, 6 is this one, right? Summation dni plus beta summation ei dni. Okay, multiply alpha and beta here. Okay, and you are adding to equation number 5, that is summation ln ni dni equal to 0. Okay, now if you see this equation, dni, they are constant or common term, you can keep it out. Okay, so you will be left with what? Summation alpha plus beta. Okay, you can write within the summation also, no problem, plus ln ni dni is equal to 0. Okay, what did I do? I just took the dni outside and the rest of the terms written in the bracket. Okay, now here note, okay, you need to note something here. dni is not equal to 0. Okay, dni cannot be equal to 0. Okay, here dni cannot be equal to 0. Okay, therefore terms within bracket, okay, within bracket must be 0. Okay, here this term is equal to 0, no? So here what we are considering, we are telling that dni cannot be equal to 0, then what must be equal to 0? This. Okay, the terms within the bracket must be equal to 0. Okay, let me write here. Okay, I am just writing the terms within the bracket, that is alpha plus beta plus ln ni is equal to 0. Okay, I just written the terms within the bracket. Okay, now what I am doing is I am keeping ln here, ln ni, and taking alpha and beta to the other side. It become minus alpha minus beta. Here I think I'll missed something. I written alpha and dni I kept here. Here beta is written. Ei, I forgot to mention or write ei here. Okay, please note. Okay, beta ei it is. Here also write beta ei. Okay. Okay. Now what you do is take the ln to the other side. So I keep ni here. When the ln go to the other side, it become a exponential. Exponential minus alpha minus beta ei. Or it can also be written as e to the power minus alpha into e to the power minus beta ei. Okay, both are same. Okay. Now this equation is known as the Boltzmann distribution law. Okay, this above equation is known as what? Boltzmann distribution law. Okay, now take the summation ni is equal to e to the power minus alpha. Okay, I am just taking this one into summation e to the power minus beta ei. Okay, summation is need not written here because this thing is a constant, no? That is why I am writing here, because here you have ei term, so summation can be written here, not here. Okay, summation ni is equal to e to the power minus alpha into summation e to the power minus beta ei. Okay, I just name this equation as equation number 8 and this as equation number 9. Now what you do? Divide 8 by 9. Okay. Now, yes. Ni divided by summation ni is equal to e to the power minus alpha into e to the power minus beta ei minus alpha into summation e to the power minus beta ei. Okay, now this get cancelled. Okay, now what is summation ni? Summation ni can be written as n also. From the equation number 1, summation ni can be written as n. So what we are left with? Minus beta ei divided by summation e to the power minus beta ei. Okay, this equation is called, or if this is the generalized form of MB law, Maxwell Boltzmann law. Okay, so this is the generalized form of MB law. Okay, this is about the derivation of MB statistics. Okay, if you have any doubt in the derivation part of the MB statistic, please let me know in the comment section. Thank you.